Thank you so much for the introduction, and thanks the organizer uh, for organizing these RAID conferences so that we can have a chance to present our work here. And my name is Nguyen, and today I am presenting our work on momentum transformer, closing the performance gap between self-attention and its linearization. And this is a joint work with Professor Richard Brannock, Professor Robert Kirby, Professor Stan Osher, and Professor Bao. So in this work, we derive the connection between linear attention and Randy-Sun step. And from that, we propose to incorporate momentum methods into linear attention to improve the model's performance. So transformer has been a state-of-the-art model for sequence processing tasks, including many challenging applications in natural language processing, speech and audio processing. And recently, transformer have been also applied on image domain, and there is very nice result for image generation using transformer model. For example, on this slide, I am showing this concept to image generations. So here we have two concepts, avocado and chair, and the transformer model will take into account the two concepts, merge them together to generate a new image of a avocado chair. It either like the chair look like avocados or an avocado in the shape of a chair. Also, people can use the transformer for text to image generation to create very creative result. So in this case, the text is a giant fruit wearing a karate belt in the snow, right? And then the model take into account this sentence as the input, and then just generates the very creative image of a giant foot wearing karate belt in the snow, which is our imagination. And finally, it can be used for text to art generation, turns a text image into a photo, an art photos. Right. So this result is so array potential of transformer for a lot of machine learning tasks, ranging from computer vision, natural language processing, and other domains. So at high level, what is transformer? So transformer is just like a neural network in the sense that it processes information from one layer to another. So the sequence input will be sent to a layer in transformer, and then the output will be the input of the next layer. The main difference between the transformer and neural network is the attention unit, which also the reason for the impressive success of transformer. So this attention unit, what it does is it takes in these input sequences, in this case have n elements, right? And then compute the correlation between these n elements in the input sequence to generate a contextual presentation for the input data. So let us zoom in to these architectures of this attention unit, what it really compute, right? So in the self-attention units, it takes in the input sequence and project the sequence into three different subspaces, Q, K, and V, where Q stands for query, K stands for keys, and V stands for value. So Q, K, and V here are matrices, and each matrix has a size of n by d, where n is the number of elements in the sequence, like number of time step in the sequence, and this is the feature dimension. So the self-attention will compare the matrix Q, the matrix carry, the carry matrix, and the key matrix to compute the correlation or similarity between different tokens or different elements in the sequence. And those similarity captured by the submap QK transpose divided by square root of D, where D is the feature dimension. And self-attention will use the contextual orientation to compute the weighted average of the value vectors. And this will be the output of the attention unit. So as we can see, even though the attention can capture the contextual presentation of the input data and improve the performance of the model. In order to compute this submax QK transpose multiplied by V, we need a quadratic complexity in both memory and computation. And just for illustration, in this figure, which we adapt from the linear attention paper from Katarobolov in 2020. So the figure show that when the sequence length increase, right, the time to process the input sequence as well as the GPU memory that the model used to process the input sequence increase exponentially with respect to the sequence length. And the experiment was done on the NVIDIA GTX 1080 Ti. So this show the bottleneck of the transformer that is this computation and memory complexity of O n square, where n is the sequence length of the attention mechanism in transformer. And this bottleneck make it very hard to scale up transformer for real-life large-scale practical tasks. So recently, in order to overcome the computation and memory bottleneck of transformer, of cell attention in transformer, a family of methods propose a linear attention. And that linear attention, what it does, it will kernelize the cell attention, right? From the submax kernel, it will write in these, it will kernelize the submax kernels, either product of two paces function, right? And then use the associativity property of matrix multiplication. It can derive an efficient formula to compute the attention. So which the kernelization and associativity property trick, linear attention is able to reduce the computation of cell attention from O(n) square to O(n), which means from quadratic to linear complexity in terms of memory and computation with respect to the sequence length. And that allows us to scale up the linear attention as well as the transformer for the large scale tasks. However, there is a problem here. So when we apply the linearization on the cell attention, even though it increased the efficiencies of the model, but it also comes with the cost of decrease in the performance of the model. So there is a performance gap between the linear attention and the full submax cell attention that people use in step-react transformer. And that's the motivation for our paper. So in our paper, we propose to incorporate momentum methods into linear attention in order to improve its performance, so that our momentum transformer inherit the linear complexity of linear attention while achieve better performance than the linear attention. So in summary, our contribution in this paper is as follows. We develop a momentum attention by integrating heavy ball momentum related ingredient into linear transformer. We introduce another momentum into the residual connection in the linear attention to enhance the model's performance. And then we derive a new adaptive strategy to compute the momentum value and eliminate the burden of fine-tuning the momentum hyperparameter in our model. So first, let me discuss our first contribution in which we introduce momentum into the linear attention in transformer, which is the linear version of this, the red box here. Before delving into the technical detail, so let me give a quick overview on run descent and then momentum methods. So we consider training a machine learning model y equal to g sub x and w, where x is the input and w is the parameter of the model, and w is, in this case, let's say it's a vector in ID. In order to train this model, we will minimize the empirical risk loss, which we take into account the training data, and then minimize the our loss function on the training data. Where here else is the loss between the predicted label and the brown truth yi given by the training set, and xi is the training data. And this is so this is quite a challenging problem, right? Because dimension d of the problem can be up to 10 to the 10, and number of sample can be around 10 to the 10, and f could be non-convex. So one of the methods that people use to minimize this empirical risk is using random descent. So technically, random descent will compute the gradient of the objective loss function, and then work against the gradient direction according to the formula. The parameter at the iteration k will be equal to the parameter w at the iteration k minus 1 subtract the step size multiplied by the gradient. And this trend descent method is, have a low computational complexity and easy to parallelize. And the conversion rate of the methods is independent of the dimension of the underlying problem. However, the trend descent might have difficulty, when, for example, the loss surface is like this value, right? Then the method can overshoot and go back and forth and slow down the convergence speed of the trend descent. So in that case, the momentum method has been introduced to increase the local conversion rate of the methods. And at high level, the momentum methods capture the curvature information, approximately capture the curvature information, use that to guide the gradient with the bus behavior of and guide the random descent with the bus behavior of the gradient. So, for example, in this case, using the bus gradient, the heavy ball will accumulate the update into the current update. In that sense, it's sum up on the gradient. And instead of jumping back and forth, it goes straight to the local minima of the block surface. Right, and that's a quick introduction review of random descent and random descent momentum. And now let's get back to our problem of linear tension. So as I mentioned before, in a linear tension, it will first kernelize this submarket kernel in cybertension into the dot product of two basic vector, and then use the associativity property to convert this, the tension computation into a more efficient form. Right. So if we look more into this, it's actually this the sum in this last slide here, right? So this sum can be interpreted, instead of instead of doing the whole sum from j equal to 1 to n, we can do it incrementally, and that will corresponding to it was similar to an update rule in a recurrent neural network. So here, instead of sum from j to n, we can sum from j to I, and then I from 1 to n, for example. And that's the linear attention can be considered as a form of recurrent neural network by introducing the two state variable si and zi, where si is the sum in the numerator of the linear attention, and zi is the sum here in the denominator of the linear tension, right? And then we can write this linear tension on the left-hand side into the incremental update form of recurrent neural network on the right-hand side. So we start with S0 equal to 0 and Z0 equal to 0, right? And at each update step, we will update the state S and state Z according to this formula. We technically, just take these Si here and add one extra term, phi kj, or like vk vj transport, right? So we write the sum here in the sum over n here into an incremental update in the form of INN update. And now under this form, we make an observation, which is the update rule here for the state S and the state Z is analogous to a random descent step, in which you can consider the state S and the state Z as a variable that we would like to find the optimal value. And this term here, phi of kj multiplied by vj transpose, can serve as a gradient, right? The information we use to update our variable of interest. So this is a observation that allows us to connect the update in linear tension into the random descent. And then what we do next is we replace the random descent update step by a momentum update step, right? So instead of just S equal to Si minus 1 plus some radial information, right? Now we introduce an extra state called B, which is momentum state that accumulate on the update from the bus, and use that to update these our variable of interest S and Z. So in our paper, we only focus on S, and Z here is just a normalization factor. So we just we just leave Z as it is and just compute S and then normalize the S. And with that, we propose the momentum attention. So in momentum attention, we introduce momentum into the update rule of the hidden state in the linear tension. And in order to speed up the training of the model, we enroll this form into an enrolling formula to compute the momentum attention, as given in the right hand side here. So I want to emphasize here a little bit. There are two forms of momentum transformer: the INN form, the incremental update form, and an enrolling form. The enrolling form will be used during training to take into the advantage of the GPU that can parallelize computation. And these INN form will be used during testing, which is when you have the new input data sent into the model, then you can use this INN form to compute the output of this new data. And the reason why we use the INN form during testing is we call it self-memory, right? You only need to have store these the hidden state each step and encrypt to update that instead of compute the whole thing, which take a lot of memory. And that's the two form of our momentum attention. And momentum transformer is the transformer that use momentum attention. So next, let me present the second contribution in our paper, which is we introduce the momentum into the residual connection in the cell attention. So let me quickly, review the computation of a cell attention here. So in addition to the attention unit with the red box here, in cell attention, we also send the output of the attention unit to a nonlinear processing, which is a neural network. And before we do that, we have a residual connection here to add the original input into the output of the attention unit. So here, that's the residual connection here. The X output equal to some linear function, some function f, apply on the output of the attention unit plus the original input. And if you look at the form of this update, again, it have a random descent form, right? Where our variable of interest is X, the input, and we want to find a better representation of X. And we do that by adding some information from the attention unit A sub x, we can be consider as the right descent update step. And with that observation, we again introduce momentum into the residual connection to derive the momentum residual connection according to this formula right here. With the beta 2-day is the momentum coefficient in the range of 0 and 1. And finally, for the momentum residual connection, in order to eliminate the burden of fine-tuning the coefficient beta 2-day here, we develop an adaptive momentum in which we can compute the momentum from the input data instead of fine-tuning that, so that we can have an efficient, a more efficient way to achieve a good value for beta 2-day instead of just fine-tuning that value using many experiments. And in order to derive this optimal momentum for the momentum residual connection, we were motivated by the problem of optimal momentum for heavy ball, right? And let's consider the function f of x to be a quadratic function with a linear gradient, right? The gradient of f will be ax plus b, where a is a positive definite. And we denote a smallest eigenvalue and largest eigenvalue of the matrix A, eta, and L, respectively. So our theorem say that given any fixed step size, gamma less than 1 over L, the optimal choice of the momentum coefficient will be 1 minus the square root of the gamma multiplied by eta square. And in this case, the heavy ball method achieve a conversion rate of a follow, right? Xk plus 1 minus optimal x star less than or equal to 1 minus square root of gamma eta multiplied by the distance between xk and the optimal value. So the theorem one shows the optimal value for the momentum coefficient for heavy ball methods. However, in general, so we don't know this small eigenvalue eta of this matrix A. So in order to handle this difficulty, we consider constructing a sequence. I follow the radian of x of xk minus the radian of x of xk minus 1 divided by the distance between xk and xk minus 1. So using this sequence, we can approximate this small eigenvalue eta. And we prove that at the limit, this sequence will converge to this up to the small eigenvalue eta of the matrix A in our theorem. In order to use the optimal momentum in the proposition 1 and the theorem 1 in the problem of the momentum attention in the momentum residual connection, we need to do some approximation to increase the efficiencies of computation. And what we do is we approximate this xk minus 1 here by the gradient information from our model, and we come up with an approximate optimal value for beta for the momentum coefficient beta 2-day at h&f as in this formula. And the projection here is just to be sure that the momentum is between 0 and 1. But in practice, we observe that when the momentum be less than 0 or less than 1, the trending is not stable. So this projection here is just to make sure that our momentum is from 0 and 1. Right. And with that, with those three contributions, let me now quickly discuss the experimental result that verifies our methods. So the first experiment we conducted on a copy task, which deal with a very long sequences, and the length of the sequence can be up to 2,000 or 4,000. Right. And we compare our adaptive momentum transformer. The momentum transformer with the non-adaptive momentum connection, momentum transformer only, without the momentum connection. We compare our three methods with the baseline and some state-of-the-art linear attention methods, such as the linear transformer and the reformer. The reformer here is use hashing technique to improve the efficiency of computing the attention, right? And on this complete task, our methods converge much faster, right, than the other linear attention. We are still slower than the submach transformer, but compared to other linear attention, we outperform them significantly in both trend loss and test accuracy. And notice that compared to the submach transformer, our method is much more efficient because we have the complexity of ON, like the linear attention, while the complexity of the submach attention is ON square, with N is a sequence. And in this case, if N is like 2000 or 4000, right, you will see the big difference between ON and ON square. And then we also test our methods on some image generation tasks on MNIST, and then later on also result for CIFAR-10. So on this task, we still see the same behavior, which is our method outperform other linear attention methods. And furthermore, we also outperform the submach attention while being much more efficient than the submach attention. So in particular, if we compare our methods with the submach attention, then the submach attention only achieves these that's bit but dim, kind of like a likelihood score, right? To show how good the image generation is. So the submach attention achieved like 0.84 bits per dim. Our method achieved like 0.80, which is better than the submach one. Why our one much more efficient? So for the submach attention, it can only generate like 0.45 image per second. Our method can generate 134.9 image per second, with the many times, maybe like 50 times, actually more than 100 times efficient than the submach attention. And then here we also evaluate the quality of the image generated by our models and the submach transformer and linear transformer. So visually, it's hard to see a difference between these church image. So in this slide, I want to show that, right, our model being efficient and can generate high quality image as the submach transformer. And similar result when we scale up our methods on CIFAR-10. So, and this is black and white image of size 28 by 28, right? CIFAR-10 is much larger. It's a RGB image of size 32 by 32 by 3. So many times larger than the and this image. And on this large scale task, our method is still able to outperform linear attention and have a performance close to the submach attention. So in this case, submach attention is still the best. We are second best, much better than the linear attention, but we are much more efficient than the submach attention in terms of how many image that the model can generate per second. We also test our methods on the natural language processing task. In particular, in this case, we test our methods for the machine translation. And on the machine translation task, we see the similar trend that our methods outperform the linear attention significantly, come close to submach attention, but much more efficient. So let me point out here in the machine translation, submach attention process like around 5,000 tokens per second. It should be it should be opposite. Sorry, there is some mistake here, right? Here, the smaller, the better. So I need to fix this one. Right. So the same story. What we try to solve is our momentum transformer outperform the submark transformer. Outperform the submark transformer in terms of efficiency, and achieve the blue score close to the submark attention, and yeah, and now blue score outperform the linear attention. And finally, we test our methods on the long-range arena benchmark, the LOH benchmark, for very long sequences, ranging from, including many tasks with different data modality. And we observe the same advantage of our methods, which is our momentum transformer outperform linear attention, come close to submark attention in terms of accuracy and more efficient. In addition to benchmark study, we are also conducting a placement study of our momentum attention on the value of the momentum coefficient. So in this slide, we consider the momentum inside the attention unit, right? And when we change the value of that momentum and see how performance of the model changes. And what we observe is the smaller the momentum used the model with better results, which is the blue curve here. We also conduct another application study on the momentum coefficient of the momentum residual connection. Right? And in this study, we try to compare our adaptive momentum with the fine-tuned momentum. The fine-tuned momentum coefficient is the one that carefully choose so that the model get the best result. And then we compare those with our adaptive methods. And we see that the adaptive momentum achieves similar, even better performance than those fine-tuned momentum coefficient in terms of trend loss and in terms of the test accuracies of the model. And with that, I end our presentation. So in summary, our contribution in this paper is based on the analogy between the recurrent neural network, formulation of causal linear attention, and random descent. We develop a momentum transformer by integrating the momentum into linear attention following the behavioral methods. And then we also introduce an additional momentum into the residual connection in cell attention to improve the model performance. In order to eliminate the burden of fine-tuning the momentum coefficient, we develop an adaptive momentum transformer in which the momentum coefficient can be adaptively computed based on the input value. And then we verify the advantage of our methods on a wide range of benchmark data set, ranging from different data modality and different size of the problem, to show that our method significantly outperform the linear attention in terms of accuracy and come close to the submark attention in terms of accuracy, but much more efficient than the submark attention. And we'd like to thank our funding agency, the Computing Research Association, NSF and ONR. And thank you so much for your attention. And I open up the presentation. I open the floor for question from the audience.